Welcome back everyone. In this lecture we will see the while group action on the set of chambers. So, let us recall the definition of the fundamental chamber and then we will make a proportion. So, recall that we have this fundamental chamber C, this is those vectors in E such that V alpha I is positive for all I range from 1 to n. So, in terms of the coordinates, if you write V equal to C 1 epsilon 1 plus etcetera plus C n plus 1 epsilon n, in this condition it says this is in C if and only if this C 1 is greater than etcetera greater than C n plus 1. So, basically these C i's are all from reals for 1 to n plus 1 and it is there here in this fundamental chamber, then if and only if this strict inequality should be satisfied. So, now we look at the action of the while group S n plus 1 and the set of chambers. So, we want to make this statement. So, W acts simply transitively on the set of chambers. So, this curly C denoted by the set of chambers. So, what is the meaning of simply transitive action? So, given C dash there exist unique. So, in other words, given C dash in C there exists unique W in W such that W of C dash equal to C, or we can also make it other way. So, W of C equal to C dash, and so this also tells that you can obtain all the chambers using the action of W on C. So, as an immediate corollary you can easily see that the number of elements in the while group is same as the cardinality of this C, which is the number of chambers. Okay. So, let us prove this. Let us start with some observations. So, we are actually interested in the general chamber. So, you take C dash to be some chamber. So, now what we can do, so we pick an element V in C dash. Okay. So, this element will look like some C 1 epsilon 1 plus etcetera plus C n plus 1 epsilon n plus 1. So, indeed these C i's they must satisfy some inequalities. Okay. Some C k will be greater than C l for tuples k l and so on. Okay. So, that is what actually those inequalities is going to define the C dash if you think about it. Okay. So, ultimately we want to prove that. So, how one can prove that? So, this given this vectors inside the C dash. So, generically how do you pick up? You pick up that the C i's, so that the C i's are all non-zero. Okay. That is how I want to actually pick up. So, then we can choose. So, we can choose W in W such that this W of V is V dash and this W V, okay, which is V dash, when you take inner product with alpha I, so this becomes greater than 0 for all I 1 to n. Okay. So, note that the C i's are some real numbers. So, they are actually there as coefficient of this epsilon 1 etcetera epsilon n plus 1. So, this alpha I is nothing but epsilon I minus epsilon I plus 1. So, this V dash, okay, some permutation of actually the V, okay, that is W of V. So, in particularly how it is done, it is just W C W1 epsilon 1 plus etc. plus C W of n plus 1 epsilon n plus 1. It just permutes the coordinates. So, if you think about it, you can always arrange this bunch of numbers n plus 1 Ci's in the decreasing order, because something is inside C if and only if the coefficients should be in the decreasing order, and we choose, okay, it is not hard to choose, okay, you choose this V so that the Ci's are distinct, okay, they are all distinct. So, I will leave it as exercise to prove this. Given any chamber C dash, you will be able to always choose this element V in C dash. If you write it in epsilon I basis, the coefficients are all of them are distinct. Because the coefficients are all of them distinct, you can find some order. So, that is find some permutation. When you actually change the coordinates, you can write it in the decreasing order. So, that is what we are doing. Okay. Once this is done, then it is easy to see that this V dash is inside C. That means, this is W of V which is inside C. So, this implies that because W being continuous map, W of C dash is contained in C. So, this is immediate, because C being connected component, C dash again being connected component. So, W will map connected component to your connected component. So, since W being invertible, that will force that W of C dash equal to C. Okay. So, once you make such choice W, then we immediately see that W of C dash must be C. So, this proves that the action is transitive action. So, you can obtain any C dash from C by applying the while group element. So, now how do you prove simple action? So, it simply act because if you take W in Sn plus 1 and then W of C equal to C, if you prove W must be identity, this implies W is identity. So, then we are done. Okay. So, this is what we need to prove. So, enough to prove. So, for some W in W such that we have, then that implies W equal to identity, and this is the definition of simple action. Okay. So, now why this is true? So, this is just true because the way C is defined. Note that if you start with a vector V in C, so you can choose V in C such that again you write it as C 1 epsilon 1 plus etc. plus C n plus 1 epsilon n plus 1. Now, C n is all increasing. Now, you can make a choice so that all of them are positive. Okay, that is always you can make, because C is consisting of all tuples which is strictly decreasing. Now, you can make a choice C n plus 1 which is positive. Now, if you choose such V, then what will happen to W V? W will be again C W 1 epsilon 1 plus etc. plus C W of n plus 1 epsilon n plus 1. You are just permuting the coordinates, but again this is supposed to be inside C, because W C is equal to C. So, that would imply that C W 1 must be greater than etc. greater than C W n plus 1, but you already have that strict order. So, but applying W after permuting, you again have that strict order. That is only possible if W is identity. Okay, nothing else will actually preserve this. So, this proves that the action of this Sn plus 1 on the set of while chambers, that is indeed simple and transitive action. So, in particularly by taking this C and applying Sn plus 1 elements, you get back all the elements of the chambers, and in particular the number of while chambers, number of chambers, that is going to be exactly the cardinality of Sn plus 1, which is n plus 1 factorial. Okay. So, we got lots of information about the set of chambers, and using this fundamental chamber we are able to get all the chambers. So, I will leave it to you to check what will be the inequalities that will define this set of the given chamber. Okay. So, you take this W c, you know that C is defined to be those C bar inside R n such that R n plus 1 such that C 1 greater than etcetera greater than C n plus 1. So, likewise W c also can be given in terms of inequalities, okay, and it is not hard to get using the action of W. So, I will leave it to you to actually get this inequalities that define W c. Okay. So, this is indeed gives us a simply transitive action on the Weil chambers. Now, what is about if you consider the Euclidean space? So, we are also interested in the Euclidean space. Now, how this Weil group is acting on the Euclidean space. Now, if you think about it, so one part of the Euclidean space is taken care, that is X. Okay. The Euclidean space can be written as X union the complement, which is union H alpha, alpha comes from delta plus. On X we know how it acts, because the Weil group simply acts simply transitively on the Weil chambers. So, that tells you how it acts on X, and we need to understand how it acts on this union of H alpha, and that is also almost clear because W is all orthogonal transformations. So, it takes H alpha to H W alpha, nothing else. So, now it is not hard to see that using this observation C bar is the fundamental region that we are interested in for the action of W on E. So, what is the meaning of that? So, given any element V in E, there exists unique W in W such that W V will be in C bar. So, that means, so given E in V in E, so this is given this V in E. If you look at the C bar intersection, the W orbit of that, so that is exactly has cardinality 1. So, I am looking at the orbit of V under the action of W, and it picks up exactly one element from C bar. So, that is what we have, okay. And this is very easy to prove, maybe I will leave it as exercise. So, this just comes from this observation. E is already written as X union the union of H alphas. So, we know how it acts on X and how it acts on this union of H alpha. Using that, one can actually get it on the E. So, that means, so given lambda in E, there exists mu in C bar such that W lambda equal to mu. So, this is what it is saying. And if you have two elements that are conjugate under the W action that comes from C bar, so then okay, so this is maybe like inbuilt exercise. If lambda mu from C bar and W in W such that W lambda equal to mu, then this forces that lambda equal to mu. One can prove something much stronger. So, if you have this situation, suppose lambda mu in C bar and W in W such that W lambda equal to mu. So, then one can prove that W must be product of simple reflections SI that fixes lambda. So, in particularly you get lambda equal to mu. You know that W must be product of SIs because SI generate the group Sn plus 1, but in this scenario you can say that it is not some random product of simple reflection SI. So, the reflections that appear in the in the expression of W, they all must actually fix lambda. Okay. So, this is all kind of more information about the while group or the reflection group that is involved. Again, this is not something we need only like lambda being mu, that is again can be proved easily using the very explicit action that we have. So, because W we know it is just a permutation. So, how it is permuting the coordinates, if you look at it, it is easy for us in this special case in type A. Okay, so, this is actually giving us the information about while group action on the Euclidean space as well as various sets, underlying sets. Now, let us see how one can actually use this to actually get the denominator identity. So, again to understand the denominator identity, we need to actually make some observation about the terms that are involved in the denominator identity. So, maybe I will write down what one needs to prove, and then later in the next class I will prove everything that is needed. So, let us look at the denominator identity, what it says. Okay. The denominator identity tells something like this: summation the sine of sigma e power sigma rho, sigma comes from Sn plus 1. The sign is being the usual sign of the permutation. So, if you think about it, Si you have identified with the transposition I plus 1, but Si being reflection, the determinant of Si with respect to some basis is going to be minus 1. So, the usual sign that you define for the permutation, so that will definitely coincide with the sign that you get it from the determinant. Okay. Either you look at the sign as map from GL of E to R. So, where given a matrix you have this determinant matrix. So, you take the sign of sigma to be the determinant of sigma, because sigma is coming from W, which is subgroup of GL of E, that is how we have identified. So, it is a simple exercise to see that this determinant of sigma is same as the sign of sigma that we define for permutations. Okay. So, this is something I will leave it to you to check. So, now what is the denominator identity says? This says that summation is equal to the product, the sum side being the sum of sine of sigma e power sigma rho. The product side being e power rho product 1 minus e power minus alpha, alpha coming from delta plus. So, this is what you have. So, the way one actually proves this identity. So, let us look at the product side. So, which is exactly e power rho product 1 minus e power minus alpha, alpha in delta plus. So, we also seen this can be rewritten as e power minus rho product e power alpha minus 1 alpha in delta plus. So, what we are going to see, so what is there on the left side, that is indeed skew symmetric, okay, because this is the alternating sum. So, whenever you change sigma by some sigma dash sigma, then you can see that the sign actually comes out from this sum side. Okay. So, that is observation that you need to first make. So, Sn plus 1 act on this pi, not only just act, and then it is act like as alternating. So, the whenever it acts, the sign will come out. Okay. That is the observation you need to make first. So, then you rewrite this product as a sum. So, this you write it as summation sum plus or minus, we need to say what it is, and then okay, maybe I will write it as a coefficient. So, some coefficient C omega e power rho minus summation alpha, alpha comes from the omega. because this is going to be just the product. So, when you take the product, the exponential will get added up. So, some C omega coefficients will pop up, okay, where omega will run over all possible subsets of this delta plus. So, this will be subset of delta plus. So, now once you have this way of rewriting, then you have to determine exactly when this C omega is non-zero, and whenever it is non-zero, what is the coefficient of that. So, we will actually exactly say that. So, it is going to be actually non-zero whenever this sum is of the form sigma rho. Okay. So, rho minus sigma alpha, alpha in omega, if it is of the form sigma rho, if and only if the C gamma is going to be non-zero, and in that case C omega is going to be exactly sine of sigma. Okay. So, that is what we are going to prove. For this we need to analyze, so where these elements actually lie and then how they are behaving with respect to the Weyl group action. So, that is something maybe I will just state it and then I will prove it in the next class. So, here is the proportion. So, what is the proportion? So, first to look at this W rho. So, how one can write? If you write W rho minus rho, so then okay, maybe you write it in the usual way. If you take W rho, you can write it as rho minus summation alpha, alpha comes from some omega, okay, for some subset omega of delta plus. Okay, we can actually very explicitly determine what is the omega. So, the omega will be those positive roots such that W inverse of alpha will be the negative root. Okay, this is what this omega. Now, the second observation, when you take something like this rho minus summation alpha, alpha in omega. So, let us call this element as some okay, C of omega, okay, for omega subset of delta plus. If you look at this C of omega, so then either it lies in one of the reflection hyperplane or it will be of the form W rho. Okay. So, the C omega lies in one of the reflecting hyperplanes H alpha, or C omega is of the form exactly W rho for some W in W. Okay. This element is exactly of the form W rho for some W in W, or it must lies in the one of the hyperplane. So, this is very important. Okay. And if you have this C omega, if it lies inside the fundamental chamber, so then that will force that omega is empty. Okay. This is indeed different only if, because rho always lies in the fundamental chamber. So, using these observations we will be able to actually prove the denominator identity. So, in the next class I will actually focus on proving this proportion, and then using this proportion we will prove the denominator identity. I will stop here, we will continue later. Thank you.